let's take a look at mathematical modeling. In this one, we're just going to kind of get a real brief overview of looking at some data and trying to figure out some patterns and seeing if we can make an equation that makes sense that we can use for predicting. So in this particular example, we have the average atmospheric concentration of carbon dioxide in various years from 1950 through 2015. Our first step is going to be to estimate the yearly increase in the average atmospheric carbon dioxide concentration. And if we look at the side, our axes and the labels, we notice that that is given in parts per million, so ppm. And that is how we will express our answer. So the first thing is, let's take a look at the end. We have 401 parts per million in 2015, and we started with 310 parts per million in 1950. So we'll do a little bit of math here. 401 minus 310 gives me 91 parts per million difference over that span of years. Take a difference in the years from 2015 through to 1950. That's a span of 65 years. So take a moment and figure out what is our average yearly change. Okay, so to get the average yearly change, we're going to take 91 divided by the 65, and that simplifies very nicely to 1.4, and the label for that is parts per million, the 91, divided by, or per year, the 65. All right, so that's how much it's changing on average per year. Let's look at the next segment. We want to make a model now that estimates the average carbon dioxide concentration, we'll call that C, in parts per million, X years after 1950. So the number I'm going to put in is how long after 1950 we are. Right? When we're looking at this trend, it looks pretty linear. So we're assuming a linear model. In this case, we're assuming the most simple equation we can. All right, so we're going to say that the concentration is equal to 310, what we started with in 1950, plus every year after that, I add 1.4 part per million. So in 1951, I'd add 1.4. 1952, I take 1.4 times 2 and add that to the 310. So in general, it's 310 plus 1.4x. All right, so we've got our model. Now the value of this is that it allows us to make predictions. So let's take a look at the third part here. It says if the trend shown by this data continues, use your model to estimate the average atmospheric carbon dioxide concentration in 2050. Well, the first thing is we have to remember that in our model here, we had to have X, all right? And X is going to be the years since 1950. Since 1950. So we take 2050 minus the 1950, and that gives me 100 that I want to use for X. That's what I'm going to use for my model. So here's our model again. Take a moment and see if you can figure out what the carbon concentration would be. All right, we're just basically putting into a formula 310 plus our 1.4 times the 100 simplifies to plus 140. Doing the math, we get 450 parts per million. All right, let's see if you can do the next one a little bit more on your own. This one's involving global temperature, average global temperature. So in this problem, the first step, just like the last one, you want to estimate the yearly increase in the average temperature, and we're going to say round it to the nearest hundredth because this one doesn't work out quite as nicely. So remember, you start with the end from the beginning, look at where you started in years and where you ended in years. All right, so let's see if we agree. We're going to take the difference of 58.44 minus 56.98. That's the difference in our temperature. And then how many years passed? Well, 2015 minus 1950. We get 1.46 divided by our 65. Rounding to the nearest hundredth, so 2 decimal places, would be 0.02. Now we want to make a model that estimates the average global temperature, we're going to call it F, in degrees Fahrenheit, X years since 1950. So you're going to start with the 1950 and add to that, because we're increasing, add to that 0.02 degrees every year. Take a moment and figure out what your model would look like. I'm going to say F is equal to 56.98. That's my starting year, starting temperature, plus 0.02 times X, because it's times every year we're going to add 0.02 degrees. And that's my model. All right, last question. The value of our models. We're going to make, trying to hide that. If that trend continues, what would we expect the average temperature to be in 2025? Well, first off, I'll give you a hint. You got to figure out what your X needs to be, because it's years since 1950, and then you use your formula. So take a moment and see if you can figure out the correct temperature. All right, so let's see what we got. X, first of all, 2025 minus 1950 means I'm going to use 75 years since 1950. From there, I put that into my formula for F, and I do the math. I simplify it, and it turns out to be 58.48 degrees Fahrenheit.